for like that, and we welcome from Maharana, talking about strategy of systems, the complex spatial dimension.
Yes, this is the pointer.
Yeah, this one is the pointer. This is forwards.
I'm very happy you could hear. It is my first visit, and I express my thanks to Linus for having me here. So before I start this talk, I want to say a few words. I have been following work of this group for quite a while because I have some interest in ODD symmetry. And generally, I want to say, think that this work that you proceed here and elsewhere is generally not very much appreciated by the community because at the moment it has gone out of fashion. And 25 years ago, it was very much in fashion. But the problem is what remains and what has been done recently is a lot of hard work, which is not understood by the street community. That originally, when we started and affected, that we showed ODD variants of the effective action. But that was effective action lowest order to alpha. And there are conjectures that this ODD symmetry holds order by order in alpha prime in fundamental theory, but it's non-trivial task to prove this because of two reasons. One is when you add terms which are ordered by order in alpha prime, there are higher derivative terms, they appear. And it actually remains to be shown that if I group together those coefficients to casting ODD invariant form. And when one look at it, okay, but beyond that, there are only very small number of groups all over the world who are persistently trying this hard job to prove this. So although I'm far away and we only came to know the correspondence, but I want to express my appreciation of this hard work being done here and only I think people of places in the world. Second, as you will see, this is also something which is out of fashion. It gets really out of fashion. And I'll spend a bit of time, not in details, but I'll try to argue that why this also merits some considerations. So what it is also, and I want to make it general. There will be some technical thing, but we may ignore and forget about it. So why? Why do you want to do this? First, now physics community, in our field agrees that physics exists beyond 4 dimensions in some higher dimensions. This is one. Second, also let us agree that there is no experimental evidence for physics beyond 4 dimensions. Theory may be consistent, but it's so if theory exists beyond 4 dimensions, some extra dimensions must be combined. At least 3 more lines of Salonga and Clyde. And those days, 1985, they wanted to unify gravity and electromagnetism. They started in the 5-dimensional case. They wanted to bring gravity plus electromagnetism, but it was soon realized by the standards. Explain real world because the experiments don't match things. Only elementary particles, so to say, were going over the electron, and of course, proton. So, many other experimental theories were proposed, and string theories were proposed, everything wanted high dimensions. Particularly, string theory, the heterotic string, wanted 10 dimensions to be consistently, perturbatively defined. So, what happens to this extra dimensions? And immediately, starting from the days of supergravity, it was proposed that we can borrow ideas of Kalinga and Klein, say that extra dynamics are compactified. Compactified has been an idea of this compactification are very small. So, in Khuri, we know more. Actually, the young people don't know are very distinguished mathematicians, really very distinguished mathematicians. And he asked this question, I think in 1995, that so he considered perturbative potential scattering and one spatial dimension was compactified on a circle. So it is a 3 plus 1 dimensional theory with one compact dimension. So he did the standard rigorous grid function method of computing scattering amplitude, and he actually tried to check the dispersion relation or the analyticity of the scattering amplitude. And by a counter example, he showed that the forward scattering amplitude is not analytic. So this is a very long paper in Analytics of Physics, and if you work it out, it is really rigorously worked out. I did not find any fault calculation, so the result stands. Yeah. So this is where I am into this game. So I was working on higher dimensional field theory, it's not field theory. Starting from quantum field theory, and I wanted to do things. One is analyticity of the scattering amplitude. Namely, the dispersion relation, and second, to derive analog of Prasad. So this was done several years back by Marcel Chaitya, and I forget the other. So they showed that total cross section flows like a side of what we call. It's bounded by
Here, actually. Oh.
also found other factors is actually sigma total is bounded by long S conductance zero square. Okay, in 4 dimensions. So D equal to 4. And they showed that fission. So they showed that sigma total in this space-time dimension is bounded by log S over S0 to the power B minus B 2. So 2 equal to 4, it equal to first half. Okay. So I am talking this, but Andre Martha told me, but this is where boundary no bound. We said why? He said, you see, they assume the converter for young people, it might be a little bit technical. They assume that the amplitude is convergent inside Lehmann-Martin helix, one. Second, they assume polynomial bounded units of the scattering amplitude. Okay? They assume. Whereas in 4 dimensions, this is actually proved. Okay? Starting from LSZ or you can go further. The convergence inside Lehmann-Martin helix is proved, and also polynomial boundedness is proved. Okay? By Gross, Epstein, Glaser, Martha. Okay. So is that true? So it means that you should prove this. Okay. So it was a formidable task, but anyway, it took me 2 years to starting from LSZ to prove these two. Then of course I derived that bound. But that's a derivation. There is no other actions. So when I went to him, he said, but you know this for they are very good friends, they have remember. Here, Niti says this. So what happens to Niti's result? So in quantum field theory, then he said, you see, if it is already in quantum field theory, then the trouble because it is very sentimental. Because they really very sentimental. If this bound is violated, then everything will fall flat on the face. And then will be very, very sorry. Because, straight lifestyle deriving this so-called toss-up, mark-up bound. So I look at so, never mind, try. Okay, so I tried. This is the history of it. So I tell you a little bit about Khuri, all of you know potential scattering, so I'll just be very quick. That what Khuri did. You can work on it. Everybody who has done the quantum mechanics course can work. It is not a big deal. Yeah. So this is how it started. So the plan of the talk in introduction, I'll talk a little bit about Khuri's work. So that might take 25-30% of the time. Well, now what I will consider a massive scalar field in 5 dimensions. There is no string theory or nothing. And then compactify on S1, okay, on a circle. And then reflecting theory, okay, is a 4-dimensional theory. So it is a massive scalar field having original mass, then kk towers. So there are technical issues that mention about. And then my sole purpose is to show that whether dispersion relation holds good, the forward dispersion relation for the resulting 4-dimensional theory, and whether the non-forward dispersion relation can be proved by this. This is my sole modest purpose. And then I will conclude this. So it might go a little bit more than 1 hour, but please decouple yourself after about half an hour, 45 minutes. Okay, don't worry. So something will be technical. Okay. So let me go back to beginning for the youngsters. So what is known? What is known is that you can say upright how we talk cross section go in strong interaction. You cannot say. Okay. So Frossa showed this actually existence of Mannstam mechanism, which has never been proved rigorously. Okay? The total cross section cannot go faster than log a square, not this. This is a constant. Then this factor usually for strong interaction in 4 pi square or 6 by another marker. That took a long time for him to. Okay? So long paper. So this, you see, in order that this is dimensionless, this actually has never been proved in quantum theory. This is actually the parameter, but generally the scale of strong interaction being 1 GeV square, so it is taken to be 1 GeV square. Then the particle data group, see, I'm also telling you nitty-gritty thing, they have fitted the total cross-section starting from accelerator energy all the way to LHC energy, and they found this to be order of 16 GeV. So this is a parameter. This is not from first principle. Okay. So what goes into this nowadays? First, so analyticity of the starting amplitude FST in the cut S plane. So we consider elastic simple cases. That is 4m square, and then this amplitude is polynomial bounded in the S plane, exactly cut. This is cross extends other. Okay, so this is bounded by S. Okay, inside a small region in E plane known as Jnanadeva ellipse. And crossing, that means A plus B going to, you say, plus B, that amplitude is analytically continued to A B bar going to A B bar. Rigorously. You can go to cross extended ladder in non-judgmental and so on. Or exchange in communication. Then we know from potential scattering there that the partial expansion is this. So this is for cos theta lying between +1 and -1 cubical region. But then they show that the partial wave expansion converges in the complex cos theta plane in a larger domain. That is actually an ellipse that was originally shown by Lemon, so the Lemon ellipse, but because of Lemon was in the Lemon mark. Unitary, okay, it's not exactly unitary, but starting from LSZ or the bigger or switching in the proof, that is not easy. So you know that steps, okay? All right. So translated to the partial wave amplitude. So if SL mode square is positive and bounded by imaginary part of our imaginary amplitude are bounded by one. So all these amplitude is filled. Okay. So this is what I said. Then you see, I said it will be a problem. So first, the scattering amplitude is the boundary value of a complex analytic in the complex square, except the cut starting from 4m square until each channel dot, okay? And this can be expanded in partial wave expansion. Where T is depending where T is momentum transfer square 2k square 1 minus cos theta angle. So you see, if you think ponder over a moment for relativistic arithmetics, you see if you want to write so the fixed T analyticity, you are in the problem. Because for fixed T, if you want to get analyticity, then as S goes to threshold, okay, then you see cos theta goes physical region, cos theta goes out of 1. Okay. So you cannot actually write this person in S.
Are we in 5D already, or this is 4D?
No, 40 order.
40.
40 order. Okay. So what Lehman did is that the scattering amplitude is analytic in a slightly larger domain, which is the ellipse, the complex cos theta. Inside that, this expansion dominant. But that problem, technical, still persists. Then we say that, well, you see, the imaginary part of the scattering amplitude appears in the dispersion relation. So let us concentrate on imaginary part. Then we showed that light in a slightly bigger domain. So it is 1 plus 2 T0 over 2k square. I told you what T0 is, 4 and pi square generally. So it is outside the physical domain. Okay. But then still there are little bit of problem. Let's not go into that. Okay. So another mark that here T equal to 0, there is a circle. As S goes to infinity, this circle doesn't shrink. So you can really for support. If you do not have mark result, then you include Greenberg no bound, which will look weaker bound than for some. Okay? So this is it. So as I told you, it is greater than 4 and not the 60 of the what? So I will try to summarize very quickly. So I do it very fast, but it does tell you. So you see in 1995 paper of he studied 3 spatial dimensions and 1 extra compactified dimension. So 4 plus 3 plus 1, but and then the radius of this compact dimension is very small, say, and so the non-spatial geometries are 3 is small. So this potential is R phi, phi is the periodicity, R belongs to small r belongs to R3, phi is S1, okay. So this potential is R goes to infinity, S into phi, R V goes to 0. Okay? Now you see, this is small appendix that in 1958 or something. Yeah, that when dispersion relation became popular, Khuri and others, they studied dispersion relation for potential sampling. and very rigorously, okay, they proved that this concentration holds good for potential scattering. Okay, but here we find something contrary to that. Okay, so this is just textbook stuff that when you write down the Schrodinger equation, you see now you have this potential VR5, that's 0, then where is this? Because the periodicity is pi, okay. N is quantized because of the periodicity, so k square is usual 3 momentum square plus 3 conserved line momentum. Okay, so this I wanted to skip, okay, so I'm not skipping, but this is all known stuff. I need to remember that Schrodinger equation is when you attend the Gibbs function, you see k square minus n square over r square x minus x prime. These are stuff. This is the extra part, and this is not nothing. Okay, and this is because of the period compactness. So then he said, it's defined, but when n square is greater than n square over r square is greater than k square, you see this exceeds. Okay, so then here the prestige of k square minus n square over r square will be minus of k. And then you see for certain values of n, this function actually is done. Okay, so large n, this function is done. Okay. So still the skip part, and you see this is what we do, potential scattering extra part is this. Okay, and then the n is the length part, the periodic part because of the compact dimensions, and this is how we define. And now some goes up here to here. Kr, largest integer is that Kr base, okay? And K prime to many. See, service. Part. Okay, so skipping all those things, the static amplitude can be extracted with your potential scattering method, and this analog of the momentum conservation is converse line mode, take out the bond part and it's two static. Okay? So okay, bottom line of all this is that you see the full Gibbs function satisfies. Okay? Then there is the compact base. And then what Khuri did, he considered good potential. The potential they had been to way back. Okay? And this is the equal type, the good behavior. Okay? If you have 1 over r potential, you will not know how to define the plane wave. Okay? So the good potential is false. Okay? For n is equal to 0, that means don't consider the 0 mode, not the convex line part. Yeah? Static amplitude analytic, but don't consider n is equal to 1, yes, the forward static amplitude is not 100. This was Khuri's point. And Khuri did not stop here. You can, as I said, this is 257. Khuri remarked that if analyticity breaks down, okay, is for non-relativistic potential scattering, in Gibbs function technique, perturbative method. So this can be explored in LHC 1995 paper. Okay. So this will have serious implications for physics at LHC. So this is a matter of concern for Angarmatha, because if this falls flat, Angarmatha himself will fall flat. If you go through his work, he dedicated all his life. Very few physicists you will see that who dedicate one for entire life practical except some ceremony of physics, all his life. And still, he's today for experimental physics and rigorous physics, that's still like a piece of diamond. Okay? Nothing has actually tainted. So he was very close to me. He treated me like his family. Okay? And he was very emotional. So he came to me and I told him what I had. Okay. So the question is, what happened quantum theory with compact fiction. Now I will make a two-line remark. So when I went to him, I told him that I'm old, I'm slow, I make mistakes, blah, blah, blah. Then after we, then it's a good thing. This is, I think it's correct. Andre, potential scattering satisfies this person relation, okay, it's very, but this has no meaning. Because in relativistic field change, analyticity and causality, they are related. Okay, very rigorously related, if you see field change. But however, in potential scattering, there is no limiting first. Okay? So if you prove or disprove, it has no meaning because relativity is not there, causality is not there. Causality and analyticity are very deeply related. So if it is violated, it is violated. So I think the way to do it into quantum field theory and implement causality. So no, you are right. So you should look into it, but you should not. So this is what I propose, that I start with 5-dimensional massive neutral picture. This is great scale. In flat space, there is no gravity. Compactified of this one. Okay. So from the 4-dimensional field, there is original massive field and KK hours. So then you have to have some assumptions. So assumption is we work in this framework of MSZ. Okay. So there will be KK hours, we take care of that, and we assume that all particles are stable, there are no bound states, the vacuum is unique. Okay, the bound state can be relaxed, okay, but I didn't want to go into that. Okay, so what do we postulate? This was the 5-dimensional theory. Okay, where the Hilbert space is exact, and don't have to repeat this. Theory will be varied under exponential mechanism, where we can have the interest of the Lorentz group. These are all 5-dimensional variables. That if you keep a diagonal state, then can actually have more proper state, right? And microcomputing. So 5-dimensional uncompactified. Okay. Now, as you go from uncompactified theory to compactified theory, so when we split X hat into X1, X2, Y, this is compact. And then you see original theory, in and out states. They are free states. Okay? They satisfy free theory. So we have this field. So now when we split like this, so in and out can be split. Okay? XY. So this is the 0 mode. Okay. Where so and the only Y dependence is here. So you see, this is the equation satisfied. Okay. And therefore, now there are tau of KK functions, N square is X square plus N square over R square. Okay, and these are in and out states. Okay, and now the momentum in the compact case is quantized. Okay, so you can say this is a charge. Okay, KK charge. So the field will be designated by a KK charge. Okay. Similarly, when we go to interacting theory, we have interacting field, so we can split the 0 mode part and the conserved part, and then we can define correspondingly the equation operator, hence the Fock space. So this is for the 0 mode, okay, and this is for the excited. So this is now Q and RPS. This here is the relation. If you have P prime, P1 prime, P1, so they are Hilbert space in 5-dimensional can be decomposed as the sum of Hilbert space designated by N. So they are all orthogonal to each other. I think this part there is no problem. Okay? If you have any problem, please ask me. Now, you see, it is rather straightforward. There will be 0 mode state. So there are 5 5 prime is equal to 5 prime. Then this is 0 mode, this is other prime mode. Okay, equal scattering. Okay, then this has no charge, this has charge, but equal. Okay, this creates unequal mass. This is charge, and different mass. This is charge, this is charge. Charge is equal. Masses are different, unequal mass scattering, and then henceforth I assume that n is equal to n prime, n is equal to n prime, so that the equal mass elastic scattering of two particles, but let's carry keep charge.
So what is chi here?
Oh,
Phi is the zero mode.
sorry. You see, phi is zero. Phi is carrying non-zero convex lines. Charge.
Okay.
If you remember your very old physics, this is like, let's say, a PP scattering, okay, or rather PP prime scattering,
So-
T delta scattering, this is like pi T scattering, okay, and this is like pi P going to sigma K scattering. Okay?
So chi of 0 is phi.
Yeah, pi 0 K theta is phi. Okay. So now I'm going to reference. So T is the momentum of phi, T is the momentum of time. So these are the scattering of the states. Okay. And then we define this. This is necessary for future reference, but we will not derive all those things. But they're necessary, and somewhere I will comment on. Okay. So define Mandelbrot equation. That's a 5-dimensional, it doesn't matter. 2 or 4. So PA plus PB square is a get PA minus PB square in this, and then MX square is an excited state which is multi-particle state but which has momentum of A. Similarly, CG. This is like consider fire with scattering, then it is m plus pi. Okay, it's two particle state, but it has same charge as the proton. And similarly, we consider M, A, B, C, D, okay, all these things. So M is the two particle state, but which has charge of both A and B. Just imagine pi plus and P scattering. So M may be like a multi-particle state which has two charges. Okay, just for bookkeeping. Okay, and this is for technical reasons required much later. I just state. Now let us consider this n is equal to 0. That means it is equal mass, zero charge, simple elastic state. Okay. So then if we put the elastic what is R? What is the R? We know the particles for future. Now look at the Clyde-Gordon operator. So this acts on this retardant product. Okay. So it acts on 3 ways. Let's look at one calculation. So first it will work on theta function, longevity type, derivative will be the delta function, and this goes inside. Okay, it will give you the calculation. Okay, so that is the actually a current, source current. Okay, and that comes like delta function I told you, comes with finite number of derivatives. Okay, of delta function when we got 2 Clyde operators, delta prime may appear other things. So this paper, this argument into one thing. To young people, I will advise take a week out. It's not such a wastage of time. Please go through Semantics 1956 paper. You cannot believe that this is the first paper of a postdoc. Okay? The first paper of a postdoc. Okay? You just cannot believe with how much of clarity and how much of rigor. Okay? This young man, he had just written the LSZ paper, the postdoc in Chicago. You will see how much rigor and clarity in semantics paper. Okay? It's like precision in thinking. What he says, of course he doesn't. He says, when that one is the and there will be a finite number of derivatives because it's local field theory. One. Second, when you take Fourier transform, what will you get? You get momentum variables. Okay? And this amplitude is Lorentz invariant. So all these things will be only Lorentz invariant variables, but they will be SPU and they will be polynomials. So we are not interested in polynomials because we are studying analyticity in there. So he kind of discards. And there will be terms which will be vector functions and commutator of field variables. It's equal time commutator. Equal time commutator of two field variables, and we have microcosines. They all vanish. Yeah, a high school student will understand when you have to go back to 56. And see, the precision of thinking of this man, but everything is derived very rigorous. So I was very much inspired. We're not wondering what this for sake of completeness, I say, so we have something like this. So when this actually operator, because we are not interested in delta function. So when this acts on team, so so you see there will be this operator acting on the fields and the source current. So this will go to R operator plus derivative delta function, we don't care. And second thing is use Lorentz invariance to write that whenever it comes something like this, you can write this x minus prime over 2. Thus, transversal invariance, prime minus x over 2, and this will come out with the transversal. Okay? So, now, you define three distributions. The Dirac function is the function and commutator of two currents, as I showed you how the commutators appear. And advanced function is the scalar function and commutator of the current. And for the see there is a zeta function commutator of current. And these are arbitrary physical states. So we don't reduce them according to the result, so we treat them as parameters. But if you take Fourier transform of this, okay, then you see this is become FZ, and look at this function, okay? So because of causality, this will vanish outside the line. Okay? And now, if you get these three functions, then FC is different from 2. It's okay? It is very simple, right? Now, whenever we have product of two operators, we know we have the completion of states or here. Because we have product of two parents, we have this, okay? And then the other competitor, we have this. Then you see, look at P1, I insert the completion of states, here I insert the completion of states. Use the same old trick of using translations, okay? So we will get this, we can reduce this dependence to z equal to 0. Similarly, we can reduce this dependence to z equal to 0. Okay, so we can write the causal commutator distribution as this. You see, this is because we have still one integration left, okay, to Fourier transform. So therefore, you see, this is on-shell physical states, by the way, in energy. And so, Pn intermediate state satisfies this momentum conversion. But yeah, no, this is also conservation law, imperative, and all, so, look at this, okay? Here, then, and the other. So, this is a deliberate details. Then you can cover, first, is this object and other one is this, okay? So you can actually, you have to go through a little bit of LSZ role, but you can say, show that S is the imaginary part of the statue. A is the other one, that's the imaginary part of the new planet. Now you see, so physical state, that you know that this one amplitude non-zero, that has to be minimum mass states, okay? This is mass gap and energy, okay? Mass gap, they are all physical states. Similarly, for the other one, you see, this has to be greater than n minus square and this has to be greater than 0. So, if you look at the it's but it comes from. Very good. This is the Analyticity now. So one part in the forward light zone, so that the integral converges. Other one in the backward light zone, so that the integral converges. Okay. So this is for these Fourier transforms to be non-zero. But where will they vanish? Okay, you see? X is equal to 0. When X is equal to 0, AS is equal to AU. And you see, this is the one vanishes. This is the another energy condition. These are unphysical regions. Okay? And I told you the reason for very physical. So, let us go to the answer where this function is A 0. So therefore, you see, in the this is the physical region and the things are non-zero. This is where the two are coincide, okay, and this is where they vanish. So the element will be unphysical region. So two functions coincide, okay? You can, because we showed that they are analytic, okay? In the forward light cone, backward light cone, so they actually coincide on physical region, okay?
What was AS and AU again?
Oh, the imaginary part of the external amplitude, imaginary part, if A, sorry, if R is the imaginary part of the forward scattering amplitude, if A is the imaginary part of the if U is the imaginary part of U channel.
Sure, but what is AS and AU again?
Just I denote them as, this was understand you at A. So these are the imaginary part of that. AS is the absorptive part of the external amplitude. Okay. All right. So you see, unphysical region they coincide. But for real values, unphysical value comes scattered. Yes. Yeah, but they are inside the light cone. So now I will not go into all those rigmarole of detail to find out what is the domain, okay, where the amplitude is free from zeros, okay, where it doesn't. So this is the, this is the Gauss-Lehmann-Dyson theorem. So we will not go into detail, but show that there is a domain in the complex plane where it's free from singularity. That was very important in order to write a discussion. So because we started from this problem, that for some unphysical to positive value, we have to find analytic topic. Okay. So I'll skip this lemon ellipse and so on, but that is a separate seminar. Okay. So now we consider the colors are client. Okay. For significant, all colors are client are same. But what is important, they carry similar line charges. And then we will see what is the problem. Now, you see, the data coming out, going by. So you color by direction, you find out operators inside tracking fields, so these are currents for the color line sources. Now, if the scattering amplitude is A plus PC, you transform. This is the forward light source, and this is the combination of two sources. Now, once we are given this, we can actually come to the imaginary part. Take one function, take the complex conjugate of this function, and we have a direction. So what is that? Well, XCC is my is Jnanadeva commutator, and then we have that theta 0 plus theta minus 1. Then insert completion of state, blah, 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 all this that we do. So this imaginary part, you see, T plus TC, we have outgoing particles, is intermediate state momentum, then T C N, the star of T N, and this scalar momentum. Time, this, and then this, okay. So this is the generalized integration. If you consider forward scattering amplitude, you will recover the optical scalar. That will be finished. Now you see, look at the first term. What is the first term? First term says that PT plus TC is intermediate state, but for the momentum consideration is PA plus T, right? So, what is that object? This is just S. You might have some idea. You can set up one. But look at the other one. I'll come back to the other. Look at it. TV minus TC equals TV. What is that? That is this delta. This delta. So, now, if you go to a Lorentz frame where TV is at rest, TV in 0, then you see Mn square is 2B, T minus TC, TC there is a 0. The second term is not permitted physically. Okay? The only first term contributes. So 0. So only of the two terms in the discussion in the optical theorem, this term contributes, this term is forbidden. Okay, now consider the cross section. Where PC is the antipart, TV minus PC, TV minus. So this is the result, this is the result, therefore you see this process can undergo. Okay? So, so see for the first one, the S channel process doesn't contribute. For the second one, U channel process contributes, for S channel doesn't. Okay? So, so now forward scattering. So you see, all incoming and outgoing moments are similar, P are same, P is same. Now the square of the triangle operator, these are the fields, they generate currents, okay? And then this becomes the x in this momentum plane. So the unit vector get along PADX. Then and this is from microcausality, F is that x equals 0 unless it's 0 difference. Okay? So microcausality is 0. Okay. So you see, we write the forward stacking amplitude like this, and look at this. Okay? Omega square minus this, and then the Fourier transform. Right? So this analyticity will be upper half omega plane. So that you from the mechanism. no branch point that anywhere is from plus minus one, you have to get this term, okay, they cancel. And this is even in R, okay? For omega, greater than omega, L in mass, that's a total, this is behavior of this function. But you see, this takes this. Okay? So you see, it's not hard to prove all this thing. Okay? So with the little bit of the so-called crossing property, that's the FR omega and WR satisfying so-called dispersive case. So imaginary part of this is dispersive. Yes. Thus, we prove a dispersiveness. Okay? So, quantum field theory is saying,
I have a question. What happens in presence of gauge fields? The
the
similar.
question you ask me when I come to conclusion, I'll answer. No, I have an answer.
Okay.
Okay. What did we get from already? The question is, can you prove non-forward dispersion? Okay? Within the mathematics. Okay. So you see, I told you this problem of threshold behavior, then we have to show existence of the lemma analysis, but these I proved earlier in my paper. Okay. So you have, okay, so in summary, using Norton's theorem and his yours lemma license available in the sense, you can show that the large lemma with this. So if you see oxidized by 1 plus e to the away, okay, this takes sigma 1 g. Lemma analysis. Okay, so then on the Norton's theorem, okay, but actually there is a small circle at t equal to 0 where function is analytic and it doesn't shrink as it goes. So you can prove this over. Okay, so you can prove the existence of lemma multiplying. Now, I have shown it in my paper, this long paper, that you can prove all these things starting from LS. Okay? There is no problem, no contact. Okay, so you see, one comment as I told you in the beginning, that if you don't prove Markman's theorem, then you not prove thoughts are bound, you only prove this by no bound, which is a weaker bound on 20%. Okay? So as I said here, at t equal to 0 and the radius r, which is doesn't depend on s, then the circle at t equal to 0. As s goes to infinity, we down shrink to 0. Okay, so we can prove lemma and full figure form. Okay, so I prove that. Crossing. Okay, now and we saw in unphysical region, the advanced distribution of the retarded distribution, they coincide. One is on the V class, this is the retarded one, and is the minus imaginary part of Q convergent, okay, and they coincide for real unphysical. Okay, this is where one invokes the so-called edge of the base theorem. We have two analytic functions or complex variables for real values of the arguments. For some real interval, these two functions coincide. Now, when we analytically continue, one goes to, let's say, S plane, okay, the S channel, another goes to U channel. So there are two different functions when we consider, but they coincide. So that if for function of several complex variables, for real values of argument, they coincide, the analytic and coincide in certain finite interval, then these two functions are analytic continuation of. So you want to scare people, you want to stop people, edge of the wedge theorem. But edge of the wedge theorem will be more than that with lot of rigor. But this is physically what we, for practitioner physicists, once you understand this, you understand what they are talking about. And when you Brahman, Amen. Like that. So in that paper, they do it in a mundane method before this, but I work through that paper and you can understand. If I understood, you will understand. It's not very hard, but it's a very, you could say, in modern times, it's a dumb way of, but they, or Taylor. Yeah, Brahman, Taylor, okay. So now this is the dispersal relation in full unit, FST, is the imaginary part of the external amplitude, okay, and the internal discontinuity and internal amplitude, and this I have written without any subtraction. That means as S goes to 0, these functions are moving. Suppose you say they don't have good behavior, then you can invoke, which I do for this compactified region or Martin bound, that this cross sections, okay, this amplitude at most can lead to subtraction. Okay? So you can write twice subtracted dispersal relation, so that is not a big deal for us. But this can be good. Okay? The Jim Martin upper bound. Okay. So then it becomes more or less trivial that all cross section is constant times log S over square. But for strong interaction processes, most of the reaction this mean for pi over T0, but for us, this T depends on the radius of compactness. Experimental. This is not proved from first principle in the sense T0 is not extracted. T0 is extracted from pi by scattering. So we don't have observation of parallel line sets, we cannot determine this. So now, okay, so I basically talk to little bit about Khuri, okay? Then I consider in LSZ form a framework. Okay, and then I consider the ERC stacking of N equal to 0, then not equal to 0 trivial, then I consider H not equal to 0. Okay, and I prove forward dispersion relation. Okay, so another mark I say, then I prove non-forward dispersion relation, so you are happy. Okay, now I will come to your good state. So we assume cellular lines charge is conserved. This is a discrete additive quantum number. Okay. Some people have questioned this point. Okay. No, we assume no bound state. Bound state problem can be solved. So, but if we have BPS states, then we will have bound state problem because BPS states can sit on top of each other with zero binding. Right? But we don't have BPS. We have no state. Okay. No subtractions, but justify. The non-fixed, fixed dispersion relation, this I do. Oh, where is your gauge? No. Okay, I maybe this have it, I'll tell you about it. What happens for gravity? That is why I consider flat space in 5 dimensions. Right? And what happens in presence of gauge field is following. If you remember, I consider existence of space n AB get another MAB square and M get, let us say, ASD square. So in finite diagram, F A B considers based on final picture. Indeed, this will correspond to this. And I put that wrong. So A C B D of the values. Now you see, make one this, because this is coming on zero. Now have quantum numbers of A plus C. Now in case of gauge fields, you see, we have two gauge fields. Okay? Having one quantum numbers of AC, but you see, there they have zero mass. Because gauge fields have massless. Okay? So then you have problem in showing existence of them on mass balance. That is why all you see in literature is such all literature, you will not find no such rigorous bound for gravitational science. That means a graviton scattering some protons. Okay, you will never find what is the total cross-section in rigorous terms. You can find low energy limit, you can find iconal summations, you can see, but you cannot find analog of it. So this is the reason.
Okay, thank you.
Now, second thing is, if you are considering gravitational scattering, then you cannot asymptotically have asymptotic states, because graviton is a long-range particle. So in the t going to plus infinity, minus infinity, you will never be able to define three states. That is the starting point of LSA. Okay? So no matter how much people talk all these things, when I see individuals, I just ask these questions. And all the people I have talked to, they cannot convince me that when graviton is involved, yet they can find in the T channel non-zero threshold. So it's a very difficult problem. So you have to relax certain assumptions to come there. If you don't relax, then you can't come there. There's no harm in relaxing, but I'm saying within that framework, I don't think it's possible. So thank you very much for your attention.
Thank you.
So I did not detain you too much, only 5 minutes.
Does anybody have any questions?
So what happens if you take more than one compact dimension? Does it change anything?
You know these things, but you can use our technique, that's what John and I did. I don't think it will create too much. Suppose we got for T2, what else is there? T2 is flat. Right? If you consider TD, then I don't think so. Well, we have done that. I think.
So recently, there have been talks about extending the definition of crossing symmetry.
Yes.
Does that somehow affect?
See, question is crossing again. You see, involves certain analytic continuation. Okay. So I have followed these words. So I don't know how much of that will stand all these criteria. So I should not come in. Because crossing is a different problem, but it also require certain rigors, because you see, you have these forward views, I have not understood it. So I should not really comment on their work, this so-called Steinman's work, right? Steinman's sphere. So I don't know, none of this paper refer to Steinman. So I don't know whether they know they don't refer, or they don't know they don't refer. So I cannot comment.
What about fermions?
Oh, fermions is just complications of spin, but then you can go to helicity instead of this simple amplitude, so you can define in terms of helicity. Well, that has been solved. Cornell and Martin. So you can start with helicity and then Maho and Martin. You can start with helicity, then you can derive analog of So it will be complicated, but it's not a very difficult concept.
So for fermions, in principle, you can have two boundary conditions, right? Periodic or antiperiodic, both are so.
Yeah, but you see, when you define asymptotic states, you have to define. So that will not pose any problem because single particle asymptotic states, right? So then, when you want to do reduction, then there are no longer three states, right? That is why when you do LSZ reduction, you get this Kalula-Klein operator starting from the interacting fields, you go there. So only single particle states and Fock states built out of the single particle states, they form a complete set of states. They're part of the Hilbert space. But we never talk to interacting fields in the remote past and remote future. Okay. So then you will have the corresponding variance.
If nobody has any more questions, thank the speaker again.
Yes.